In this video, you will answer your bell ringer, review on the role of the sun in driving the convection currents in the atmosphere and ocean. So here are two maps. You will have to determine whether they're high pressure or low pressure, good weather or bad weather. Happy answering! In summary, say aloud the symbols of low and high pressures and the weather they bring. So, low pressure is L, high pressure is H. How does the sun affect weather? What drives the convection current producing winds and ocean currents? Yes, it's the sun. Because of the sun's uneven heating of the Earth's surface, different weather patterns may occur. Because water has such a high heat capacity, ocean currents have the ability to carry large amounts of heat energy from the tropics to the temperate and polar regions of the Earth. Generally, surface currents carry warm water from the tropics to the polar regions and cold water from the polar regions back towards the tropics. Ocean currents have a significant effect on global and local weather patterns. Cold ocean currents would have cooling effect, warm ocean currents would have warming effect. As can be seen here, you have the Great Ocean Conveyor Belt pictured in this image. These belts are the major ocean currents that move warm water from the equator to the poles and cold water from the poles back to the equator. Now let's talk about weather fronts. Listen and watch.
In this film, we'll see a demonstration that will help to show what happens when warm air meets cold air in the Earth's atmosphere. We'll use water to simulate the behaviour of the air. I put tap water into this tank. Now I'll add this plastic gate in the middle to divide the tank into two halves. Next, I'm going to add some warm water to this side and some cold to this side. I've also dissolved some instant coffee granules in the cold water so that we can see where it goes. Now I'll pull out the gate and we'll see what happens. They don't immediately mix together. Instead, the lighter warm water rises and overruns the cold. The more dense cooler water sinks and undercuts the warm water. Notice that the movement is one way at the top and the other way at the bottom. Something similar happens to the air in the Earth's atmosphere at a front, a boundary between warm and cold air.
Welcome to Moo Math and Science. In this video, I'd like to talk about 4 types of fronts that create some of our weather. Air masses that form from different areas often do not mix. The reason is that the air masses have different densities. For example, warm air is less dense than cold air. So when two types of air masses meet, warm air generally rises. The area in which the two types of air masses meet is called a front. The four kinds of fronts are called cold fronts, warm fronts, occluded fronts, and stationary fronts. Cold front. A cold front forms where cold air moves under warm air, which is less dense, and pushes the warm air up. Cold fronts can move quickly and bring thunderstorms, heavy rain, or snow. Cooler weather usually follows a cold front because the air mass behind the cold front is cooler and drier. And here's the symbol for a cold front. A warm front forms where warm air moves over cold, denser air. In a warm front, that warm air gradually replaces the cold air. Warm fronts generally bring drizzly rain and are followed by clear and warm weather. And here's the symbol for a warm front. An occluded front forms when warm air mass is caught between two colder air masses. The colder air mass moves under and pushes up the warm air mass. The coldest air mass then moves forward until it meets a cold air mass that is warmer and less dense. The colder of these two air masses moves under and pushes up the warm air mass. Sometimes, though, the two colder air masses mix. An occluded front has cool temperatures and large amounts of rain and snow. And here's the symbol for an occluded front. And finally, a stationary front forms when a cold air mass meets a warm air mass. However, the both air masses do not have enough force to lift the warm air mass over the cold air mass, so the two air masses just remain separated. This may happen because there is not enough wind to keep the air masses pushing against each other. A stationary front often brings days of cloudy, wet weather. And here's the symbol for a stationary front. So there we go, 4 different fronts that create some of our weather. Thanks for watching.
To understand why the US coastline is so vulnerable to hurricane strike, you have to travel over 4,000 miles east to the place where hurricanes are born. Most hurricanes in the Atlantic begin as very small atmospheric disturbances in the jet stream that flows from east to west over sub-Saharan Africa. Scientists call this disturbance an easterly wave.
What triggers the development of an easterly wave could be anything. Could be a little girl playing in the sand. It trigger off a little dust devil, for example, that perturbs the atmosphere downstream in such a way that you get one of these waves.
The easterly wave creates a system of turbulent eddies, which go on to develop into a cluster of thunderstorms. These travel west across the African continent and then encounter the warm tropical waters of the Atlantic.
One begins to see on satellite pictures is these thunderstorms appear to become better organized and begin to rotate around each other. The rotation rate increases, the storms become more vigorous, and the winds continue to increase.
The storm rapidly gathers strength and develops into a hurricane, feeding off the warm, moist air coming from the ocean.
The heat is coming out of the ocean. The hurricane heat engine converts that heat energy into the mechanical energy of the winds. And that's what's powering the storm. When the winds reach typically around 70 miles per hour, the storm may develop an eye, surrounded by an eye wall, which is a region of very intense heat and the strongest winds. And you're off and running.
These are the hurricanes that make landfall on the US every year, causing enormous damage.
Hurricanes are very large and intense storms. But where do these giant storms come from? A hurricane starts with the warm water found near the equator. Hurricanes typically only form in tropical regions where the ocean is at least 80 degrees Fahrenheit. These warm waters evaporate, creating warm, moist air which acts as fuel for the storm. Wind is also needed for a hurricane to form. Many hurricanes in the United States are caused by winds blowing across the Atlantic Ocean from Africa. This wind causes even more of the warm water to evaporate into the air. The warm, moist air then rises high into the atmosphere, where it begins to cool. Way up there, the water vapor condenses back into liquid water droplets. Water droplets in the atmosphere form clouds, including big, stormy cumulonimbus clouds. As the warm air continues rising upward, the winds begin blowing in a circular pattern around a center. The spiraling winds gather up a cluster of big thunderstorm clouds. Once the spinning winds reach 74 miles per hour, the storm has officially become a hurricane. Hurricanes are huge. They can be 10 miles high and over 1,000 miles across. Once a hurricane hits land, it runs out of warm, moist air and its winds begin to weaken. But the storm can still cause lots of damage to communities near the coast. Thankfully, we have weather satellites that are constantly monitoring the conditions down here on Earth. The GOES-R series of weather satellites scan the hemisphere every 10 minutes and the U.S. every 5 minutes, keeping an eye on conditions that might cause a hurricane to form. Once a hurricane forms, the satellites can help predict the storm's intensity and track it minute by minute. This information allows meteorologists to deliver early warnings and help people stay safe.
Weather maps, also known as the synoptic chart, are an example of an isoline map. Isoline maps are made up of lines that join points of equal value. Contour lines drawn on a topographic map are another example of an isoline map. Weather maps use lines called isobars, plus other symbols to join together lines of equal air pressure. Today, most meteorologists use the hectopascal for measuring atmospheric pressure. Many weather reports to the public use the millibar. 1 hectopascal equals 1 millibar. On these American weather maps, the isobars are drawn at intervals of 4 millibars. 1013 millibars is the average sea level air pressure. Therefore, areas with an air pressure of over 1013 millibars are considered to be areas of high pressure, and areas with an air pressure below 1013 millibars are considered to be areas of low pressure. On a weather map, areas of high pressure, or anticyclones, are identified by a letter H. These areas are associated with clear skies and little wind. Areas of low pressure, or depressions, are usually identified by the letter L and are associated with rain, clouds, and high winds. High-pressure systems have enclosed isobars which increase in pressure towards their centre. Low-pressure systems, on the other hand, contain isobars which decrease in pressure towards the centre. When isobars make a sharp bend around a low, this bend area is called a trough. One of the main symbols employed on a weather map is called the front. A front represents the boundary between two air masses and appears on the weather map as a line with triangles or semicircles attached. Generally, wind flows towards the centre of low-pressure systems and away from high-pressure systems. When isobars are close together, wind is strong. When isobars are far apart, wind is weak. Now it is time for you to go and read some weather maps and see if you can interpret them.